Hi everybody, and welcome to another video installment brought to you by PLCGurus.NET. So today what we're doing is we're launching a brand new YouTube series that's going to hone and focus in on Logix PIDE implementations. So this is definitely a more advanced topic, and I do strongly encourage, if you haven't watched our Studio 5000 Essentials video series, that you go ahead and run through that series first, so you're competent on the Logix programming side of things. And what we aim to do in this video series that we're going to title Logix PIDE Essentials is dive into a practical implementation of PID, the PID enhanced instruction specifically, and how we can go about implementing that in a Logix controller. So you're probably looking at the screen wondering, okay, what is this guy going to be throwing at me here? But I want to take a few minutes really just to review the underlying algorithm that any PID controller is going to use. And the Rockwell implementation of a PID controller is no different from this. There is a slight variant that we'll take a look at here on how Rockwell actually implements the classic PID equation. In a nutshell, it's very, very close to the classic mathematical implementation of it, okay? And I do want to point out down here, before I do even get started into this, is that I did do an in-depth article that you can find at this link here. I'll include a link in the comment section below as well. If you want to go ahead, I do actually highly recommend that you go ahead and read through that article at least once, okay? Because I'm not going to go into the kind of depth, at least up front, that you're going to need. I want to give you a little bit of information. We'll do a little bit of programming and then jumping back and forth, okay? So this set of slides is going to be something that we'll refer back to quite often, most likely, okay? Like I said, there are two classical PID, mathematical PID equations that you're going to see. You're going to search the net, you're going to see all of these different variants of these fundamental equations, okay? So there's something called the classic dependent PID equation, which takes on this form. And I'm not going to get too heavy into the control theory side of things here, guys. I want to get you proficient on how to implement a PID. I mean, control theory is a whole set of courses that you could take at an advanced level. That's not what we're doing here today. But anyway, so there's a dependent form, and this is what it looks like, okay? So we have K values here. You can see KC is actually your controller gain values. And then we have something called the independent equation, okay? And really, the subtle difference between the two is I want you just to focus in on these K values, okay? So you can see here in the independent equation, we have a KP. This would be your P term. We have a KI. This is your I term, and then we have a KD value. So these gains are independent of each other, which is why they call it the independent PID equation. Now, looking up at the dependent form equation, you see something very common here, and the commonality is the controller gain here. So we no longer have independent gain variables here. We actually have a common gain value K in KC, okay? And you can see here we are doing some integration because we are looking at a change in error with respect to time. So we have some derivative action, we have some integral action, and again, I'm oversimplifying some things here just for the sake of brevity and the sake of practical implementation. But you can see we have a T sub I and a T sub D term here, and these become the actual terms that we will be manipulating, as well as KC, in the Logix PID controller, okay? So you can see here, well, let's just do something here. So I'm going to go ahead and break this up into a couple of pieces for you. So you can see here, if I looked at the classical equations, these boxes represent, so this box here in each term is your proportional action. This box here is your integral action, and this box here is your derivative action. So like I say, if you want more in-depth information on what these different terms do, go to the article over here, okay? Now I want to draw our attention over to the Rockwell variant of this PID equation, okay? So there are some subtle differences. So First of all, you see we have a U of t, of course, that's a mathematical expression with respect to time. Here they actually name it CV, okay? So CV stands for controlled variable, and it's going to make a lot of sense when we get over to the Logix PID controller, and they actually name the output that's going to be controlling our valve, and we are going to model a process, and that is the CV, the controlled variable, okay? And the N is going to represent the scan. You can think of N as the scan, okay? So on some nth scan, your output is going to be this, okay? Then if you look at the PID expression here, or their variant on the PID expression, you can see it's actually using the previous scan's CV value and then adding in all of the proportional integral derivative action to the previous value to get your new resultant value, okay? So you can see here Kc in effect, if you look at the classical equation, all we've done here is factored out Kc, and it becomes a scalar or multiplier to the other gain terms, okay? And that is convenient for us because now once we've set up the P, the I, and the D, if we're implementing a full PID control, which we don't have to do, there are P-only control. I mean, there's drawbacks to P-only, of course. There's PI, and most implementations in industrial processes are P plus I controllers or PI controllers. And then, of course, there's full-blown PID controllers. And this is where you get into servo motion, this type of thing, okay? So we're going to be implementing it as a PI controller. And maybe when we get into some auto-tuning, we will see that it actually adds a little derivative action in there for us in an auto-tune procedure. But we'll take a look at that. We're going to go baby steps here. So you can see here the independent form, again, really looks very similar to the classical equation. Again, we're using the previous CV value to compute the next value. So it almost is recursive in nature. And then we have the Kp, Ki, Kd values. So with that, there's your PID terms in this equation, okay? And what I want to do is I want to forget about all of this stuff, and we're going to focus in on the dependent variant, the Rockwell dependent variant. Now, both dependent and independent equations will give you good PID control, and there are some differences, and I've glazed over some of those differences other than the obvious one in the gains. But what I want to do, most of what I implement in the field is a dependent form equation, and there is actually a checkbox or radio button for us to select in the PID controller in the Logix software which implementation we're actually selecting here. Okay, so we're going to focus in on this equation for the remainder of the course here. Okay, so we can actually even simplify this maybe a little bit more, and here is our dependent form equation here. And I should point out here that the error equals the set point minus the process value. That's how the error here that you see in the equation is determined. It's just your SP minus your PV. And I want to do something that might help simplify things a little bit for you. Okay, so I want to express this equation in terms of the gains that we're actually going to use or adjust to try to tune in our PID controller. So if I rewrite this expression in the form of the controller gains that we're going to be able to adjust, this is what it's going to look like, okay? So I'm just simply substituting Kc for the P gain, and this will make more sense when we get over to the actual implementation in the Logix software. There's actually a proportional integral and derivative gain setting that we can adjust. So if you think of it in terms of this, it may be a little bit easier to correlate what we're adjusting and the impact it's going to have on the overall output that we're driving here, the CV. Okay, so again, Kc is represents our controller or proportional gain, and we're simply multiplying that by the change in error. And then this I term here is represented here again. Okay, so the delta E becomes the Kc, right? P. Now remember, I put I gain on the top. But keep in mind, when you adjust I gain in the controller, it's actually 1 over tau sub I, okay? It's the minutes per repeat. So I gain, in effect, is 1 over tau sub I, which means when we go and adjust I gain in the Logix controller, if we make I gain larger, we're actually making T sub I or tau sub I larger, which means the overall gain term is getting smaller. Okay, I don't want to confuse you too much, But keep that in mind. And again, we're going to refer back to the slide, I think, several times throughout the process here. But just keep in mind, I gain is actually a 1 over tau sub I expression. So the smaller we make I gain, the larger the integral term becomes. Okay, let's leave it at that for now. And then, of course, the D term here becomes your Kc, because Kc is multiplying all three of these Pi and D components, becomes your P gain multiplied by your tau sub D, which is your D gain, and then we're just substituting the delta E over delta T. Okay? So I hope that makes sense. At least, again, it'll help us get started. I don't want to, bog us down too much with all of the mathematics, but it is important that we understand how the PID controller is being implemented under the hood. I think this is going to help clarify things. And again, please do read this article. It's very important. So now let's take a look at the process that we're actually going to model throughout these next set of videos. So if we break this Rockwell dependent form variant of the equation down a little bit simpler like we have here, we can see very easily where the Pi and D terms are. And again, remember, we can implement any combination of these Pi and D algorithm because it is an additive expression. You see that there, right? And like I said, we are most likely going to be implementing it as a PI controller. And like I said, when we get into the auto-tuning portion, I think the controller will find an optimal D component to give us some derivative action. Okay? All right, so let's move on here. So here is an abstract view of the process that we are going to be modeling. So I want to look at it kind of abstractly first, and then we'll dive into a specific example of this implementation. Okay, so this is the general form of a first order plant that we are going to control. So we have a set point that we're going to be feeding into our PID controller, and then that PID controller is going to be outputting an output CV to control the process, okay? And we're going to be continuously monitoring the feedback of that process via the process variable PV, which is most cases is some kind of sensor, and it's going to feed that back into the PID controller. And the PID controller is going to look at the set point, look at the process variable, depending on how you're implementing, whether it's direct or reverse acting. But most likely it's going to subtract the process variable PV from the set point to compute the new error. And then that new error is going to get pushed through the PID algorithm up here and compute a new controller output value for CV. Okay, so that's all it's doing. It's it's measuring the error, and I know I'm flipping back and forth here, but it's measuring the error between the set point and the process variable, computing that new error, pushing that error through the implementation that you've chosen in this equation, and then computing the new CV value. And it's doing that every scan. Okay, so that's what it's doing, and then it's making a change. We're going to be seeing the impact of that change via the process variable, feeding that back, checking the error, computing a new value, and it's doing that continuously. Okay, so that in effect is what PID is and continuous measurement is, and closed loop feedback control. Okay, and you notice here I have something called a disturbance. So we are going to provide a mechanism for us to inject an external disturbance or hit our process with what's called a step change, okay? So we are going to introduce some kind of disturbance into the process so that we can measure the dynamic response of the controller, okay? Now, I know I'm getting a little bit ahead of ourselves here, and I'm throwing some terms at you, but it's important that we see this, okay? So again, we want to know if our process gets hit with some kind of disturbance, how our process is going to react to that disturbance, okay? All right, so again, read the article, become a member, read the article, so you're up to speed on all of this. Okay, so now let's look at a more specific implementation and what I actually want to model in the Logix software itself, okay? So let's look at that. So what I want to do is, so let me just read that. So our goal is going to be to use continuous closed loop feedback to precisely control the temperature of a processed liquid in a vessel by way of a steam valve. So here's our vessel, okay, and it has some processed liquid. Don't worry too much about the motor. I found this image online, so it's closely resembling what we want to do. So we have a processed vessel. We're going to ignore the agitator motor here. With a liquid, we have some kind of thermocouple or some kind of temperature transmitter that's going to be giving us a feedback to our controller. Okay, you can see that there. And the temperature indicating controller here is in effect our PID controller. Okay, so we have a vessel with a processed liquid. We're using let's just for argument's sake say it's a thermocouple. That's going to be giving us our temperature feedback of that processed liquid. And how we're going to be controlling the temperature of the processed liquid is using steam in the steam chamber to change or maintain the temperature via this steam valve. Okay, so again, processed vessel, processed liquid, thermocouple giving us temperature feedback, and then the controller is going to be outputting a value to vary the position of the steam valve to add or subtract more or less steam to maintain set point. Okay, so I hope that's clear. So again, this is what we're going to be actually modeling in the controller. And yeah, I'm excited to get started. So again, if you have any questions about this video, please leave it in the comment section or post to our forum over on https://PLCGurus.net. Again, this is going to be a more in-depth and advanced set of videos, all aiming how to efficiently implement a Logix PID instruction and then set up trending to actually be able to monitor the dynamic response to a changing input. Okay, so I hope you found this video informative. Please subscribe to our channel, like our video, and we'll see you in the next one. Thanks for watching.